Hi, Prasid here. Let's jump into today's topic. Today I'm going to discuss about your mobile. Not only mobile phone, it can be your laptop or any kind of smart wearable device or any kind of processor you are using. Actually, I'm going to talk about chip or integrated circuit inside your device. If we consider Apple's A series chip, it is taking size of my thumbnail. Inside this thumbnail size chip, there are more than 20 billion transistors. Can you imagine a size of one transistor? It is smaller than a virus cell. Each of these virus cell size transistor has to switch on and off billions of times second to do your day-to-day activities like placing a call, taking a photograph, or doing any kind of calculation. In day-to-day life, you are taking your phone out of your pocket and using it very simply. But there is extraordinary complexity behind this development process of chips inside that. Today I am going to fill that gap between simplicity you are using and extraordinary complexity behind this development process. Everything starts with silicon dioxide. Yeah, so-called sand, common sand. How this kind of grain of sand became this kind of really extraordinary complex chip. It's taking more than a year. More than 7-8 countries are involved in this process. Dozens of companies are involved in this process. This is actually a global process to convert this grain of sand into this kind of complex chip. So, as I explained earlier, everything is starting with silicon dioxide. But we can't use any silicon dioxide which we can find. As you all know, most of the surface of this earth has covered with silicon dioxide, which means common sand. But those sands are not qualified for this process. As you know, this is really complex and sensitive process. To qualify for this process, there should be extraordinary purity level. So we can set it as there should be more than 98% to 99% of purity, or more than 98% to 99% of silicon dioxide should be there in this sand. Those sand we are calling them as HPQ, high purity quartz. Those sand can be found in very handful places around the globe. Those places are North Carolina, USA, and few sites in Australia and few sites in Norway as well. After we obtain this HPQ, high purity quartz, we have obtained initial purity level of silicon dioxide. But our target is to obtain silicon from silicon dioxide. To obtain silicon, we are doing some combustion inside electric arc furnace with carbon sources. The reaction will be silicon dioxide plus carbon. For carbon here we are using carbon source like coal or wood chips, carbon sources like that. And temperature will be around 1900 degrees of Celsius. This process we are calling this as carbothermic reduction. Those resultant will be silicon plus carbon monoxide. After this carbothermic reduction happens, silicon dioxide plus carbon sources will result silicon plus carbon monoxide. Only solid item inside this furnace will be silicon. This process strips away oxygen from silicon dioxide and silicon will be resulted. As we require, now we have obtained silicon. Inside this silicon, obtained silicon, there is purity level of silicon more than 98% to 99%. It's good number. It seems impressive. But it's impressive and it's really good purity level for industries like aluminium industry or any kind of metal industries. That's good purity level for those industries. But in electronic industry or semiconductor industry, still this silicon is not meets standard purity levels. This resultant silicon, we are calling them as metallic grade silicon. Now our requirement is to create electronic grade silicon from this metallic grade silicon. To convert this MGS, metallic grade silicon, into electronic grade silicon, which means silicon which is having silicon around purity of 98% to 99%, we have to convert them to silicon which are having 99.97, which means also together 99 should be there. That's the purity level we are expecting. To achieve this, we are creating some kind of solution called trichlorosilane, which means HSiCl3, using that metallic grade silicon. Then that is a liquid solution, and liquid solution will be going through distillizing towers to distill and obtain purity from that. We are repeatedly distilling this trichlorosilane and purifying. Finally, the resultant will be deposit inside these reactors as 9N purity silicon. After this repeated distilling process, this resultant silicon will be deposited inside this reactor as silicon rod. Yeah, now we have obtained silicon with 9n purity. We calling this purifying process from metallic grade silicon to electronic grade silicon as Siemens process. Yeah, now we have obtained our required purity level. The guardians of these purity levels are Alchemy, Germany, Hemlock Semiconductors, USA, OSI, South Korea, and Daqo New Energy, China. Those are the companies who are responsible for this kind of purity process, which means getting ordinary silicon dioxide or after getting high purity quartz and making them into electronic grade silicon, which means silicon with 9n purity. This resultant polysilicon, which is having 9n of purity level, is polycrystalline, which means there are grains of atoms in different orientations and packed together without proper order, and atomic boundaries are scattered. Not those atoms are in different and various orientations without proper crystal lattice. But the requirement is proper single one crystal lattice from one end to other end. To obtain that kind of perfect crystal lattice, the process we are following is CC method. To obtain single unbroken crystal lattice, initially we are melting this polysilicon inside quartz crucible at the 1412 degree of Celsius temperature, which means exactly silicon's melting point. We are melting that resultant electronic grade silicon inside quartz crucible. Inside that, now we are having melted silicon. After we melt in this silicon, we are getting seed crystallized silicon, which means the already created silicon which is having single unbroken crystallized lattice structure. We are getting that silicon crystal seed and dipping it inside to this quartz crucible, and we are withdrawing it by rotating. When we are rotating and withdrawing this seed crystal material, melted silicon will be solidify around that seed crystal material. While this melted silicon is solidified around this seed crystal material, it is mimicking same crystallized lattice structure of that seed material. After we withdraw in that seed material away from this melted silicon crucible, all those silicon will be solidified around that seed material, and resultant will be perfect crystalline silicon, which is having perfect crystal structure. And as the last step, before this silicon completely solidifies, we are adding some kind of impurities like boron or phosphorus to create base semiconductor base type, which means N-type or P-type. We are adding dopant as boron to get P-type semiconductor, and we are adding phosphorus to obtain N-type base semiconductor type. Yeah, before completely solidifies, we are defining the base type NOP of this silicon. This is having weight around 300 kilogram and diameter of this cylinder is around 300 millimeters. Now we are having cylinder which is having weight of 300 kilogram and diameter of 300 millimeter, which is calling as silicon ingot. As next step, we are cutting this ingot into slices which is having thickness around 1 millimeter using diamond wire saw. After these slices, which means wafers are created from this silicon ingot, we are doing some post-processing steps. First step is lapping. Lapping means mechanically removes any kind of grains or any kind of imperfections on the surface. And the second step is chemical etching. In there, we chemically remove any kind of surface issues and if any kind of grains on the surface. Then as a last step, we are doing chemical mechanical polishing to obtain mirror-like polished surface. This should be completely flat and mirror-like polish should be there. To get some kind of idea about precision of this surface, this mirror-like flat surface, if we imagine this 300 millimeter wafer to size of a city, the highest building on the city should be size of a coin. Which means if there is a city and the highest place in the city is size of a coin, then the city is completely flat city. That kind of flatness should be there. And the final resultant product is wafer with having mirror-like flatness and polished surface. Now we are having mirror-like polished wafers. If we consider who are the manufacturers of these kind of wafers, there is a wafer oligopoly between few Japanese companies like Shin-Etsu Chemicals and Sumco. And further to that, there are Global Wafers Taiwan and SK Siltron South Korea as well. After we creating this kind of mirror-like surface wafers, now we need to print our silicon design on the top of this wafer. To print a design, initially we have to create a design. In this design, we have to map billions of transistors, more than 20 billion transistors inside this thumbnail size area. To do that, there is huge design process. Initially, we are doing kind of getting a specification of our requirement, system requirements are obtaining, and obtaining different IPs we required. It can be CPU IPs or GPU IPs. We are defining those IPs, and specifications also we are defining what kind of specs should be there. Yeah, initial step is defining the design, which means we are bringing our idea into some kind of a structure. Then the next point is we are defining that design using RTA, which means register transfer logic. That is the language or we are using to define any kind of system specifications. After we creating our RTL, we are doing some kind of verifications or simulations to validate our RTL. Then as next step, we are synthesizing this RTL into gate level netlist, which means cells like gates or flip-flops like that. The next step is place and route, which means we are placing that cells with exact wiring structures and placements. Then we are doing different physical verification steps, and final output will be GDS2 or OSIS file which contains system layout. Before creating that, we are doing some kind of a static timing analysis to check whether are there any timing violations are there, or there can be some simulation, emulation or prototyping stages, because this creation process is costly. Then before doing manufacturing, generally most of the companies are doing, there are tons of emulation and prototyping steps are there. Each part they are emulation means some kind of hardware accelerated simulation steps in actual FPGAs, and prototyping is also using FPGA based prototyping is also using FPGAs based prototyping platforms and prototyping the system before sending to the tape out. Yeah, as a final step, after going through all the design processes and simulations, emulations and prototyping things, after all of that, resultant will be GDS2 or OSIS file. As I explained, this design flow is doing by any kind of designers. As you know, Apple, Nvidia, there are several chip and mobile device designers. If we consider their business architectures, those designers, first part is the fabless companies. As you can see here, in the fabless companies are only architectures. They are not having fabrications. After those design process, they are sending their layout files to foundry and creating their chip or integrated circuit from those foundries. The second type is integrated device manufacturers, which is called IDM. The companies like Samsung and Intel, they are doing their design part and the fabrication part as well. The Samsung, Intel, Texas Instruments and Micron are these kind of companies. The third type is the foundry, the pure play foundries. They are only working as foundries, as TSMC. They are getting others design and doing front end and back end fabrication part for those companies. If we consider examples, Apple and Nvidia act as the fabless companies, and Samsung and Intel and Texas Instruments, those and Micron, those companies as integrated device manufacturers, and TSMC is acting as full play foundry. If we consider Apple's and Nvidia's case, they are creating their designs, and in the tape out process they are sending those layout files to foundries like TSML, and inside their Apple's chip is manufactured inside the TSMC Taiwan. Further to these different kind of manufacturers, there are other roles as well. As I explained earlier, in chip design flow, for each and every step, those designers can't get pen and paper and do their design and draw them in a kind of paper. There should be tools in each step, as simulation and place and route and physical verification, different kind of verifications, and before going to foundry, if they are doing any kind of emulation or prototyping, in each of these stages, EDA tools are supporting for designers. Without EDA tools, they can do nothing. There are oligopoly in EDA industry. Mainly Synopsys and Cadence are EDA tool providers. Further to that, Siemens EDA is also playing a big role there. If we consider EDA industry, 75% of the industry is taken by Synopsys, Cadence and Siemens EDA companies. Further to these EDA companies, there are IP providers. Also, as I mentioned earlier, Synopsys and Cadence also providing different interface IPs. Further to that, ARM is providing CPU and GPU based IPs. Yeah, further to these earlier discussed designers, there are huge role playing by EDA companies and IP providers also in this chip design process. Now we are having mirror-like polished wafer and GDS2O design files. Now, as the next step, after Foundry receives those design layout files, as a first step, they are doing data mask preparation, which means using the digital layout data, they are creating instruction set for create stencil, which means photo mask, some kind of instruction set creating using digital layout to create photo mask. In this step, the thing is happening is they are using in this step, the foundry is creating a photo mask. They are using that photo mask to reflect that EUV beam into this wafer and print the required design. Before do that, initially they are spoon some kind of photoresist liquid on the top of this wafer, and after that they are keeping that photo mask and then hitting that ultra UV beam on top of that photo mask. Then the required design will be printed on this mirror like polished wafer. Here you can see that how this kind of design is printed in the wafer in very small area. There should be 2 nanometer scale equipments, 2 nanometer scale features should be printed on the top of this wafer. In here we can see the machine which we are using to do this process. We are calling it as EUV lithography machine. ASML is creating this kind of lithography machines. Its cost is around, for high-end ASML's lithography machine cost is around $350 million to $400 million for the latest 2 nanometer, 1.4 nanometer ready lithography machines. Here you can see that it is using extreme ultraviolet with high numeric aperture. Yeah, you can get some kind of idea about size of this EUV lithography machine. Using this figure, it's actually bigger than the size of bus. There are different perfectly polished angled mirror to reflect these high extreme ultraviolet wave beams, to reflect them and fine tune in those beams, and finally it is going through photo mask and print the required design on the top of wafer, which is covered with those photoresist liquid. ASML Netherlands is having monopoly in creating this kind of extreme ultraviolet EUV lithography machines. The only company which is creating this kind of lithography machine is ASML. After the design is printed on the top of wafer, then as the next step, as I explained earlier, we are applying photoresist liquid on the top of this wafer and printing the design. As next step, we are cleaning unwanted silicon parts, which means not protected silicon parts from this wafer. This process is called as etching process. After the etching process, we can clear all the unwanted unprotected silicons from the wafer, and as next step called atomic layer deposition, which means this process is the process which is creating exact gate structures, which means creating transistor gates, and those component creating part is that atomic layer deposition. Here one by one atoms are created one by one, and insulation process will be also happening in that process using atomic layers. Main tool makers of this process is in etching, and those, if we consider the etching part, and those chemicals are supplied by Applied Materials and Lam Research, and this process front-end fabrication and transistor creating process are done by the inside foundries like TSMC, Samsung foundries and Intel foundries like that. This is the front end of the line, which means creating transistors on the top of wafer. After the front end completed, we have to go to the back end part, which means it is not enough to create transistors on the top of wafer. These transistors should be connected to each other and should be communicated between those transistors. So to do that, we have to have communication layers, which means connections should be there. In the bottom layer, we can see the front end of the line, which means the transistors which we have created in early step. Then we are having 15 to 20 layers of back end, which means connections on the top of that front end. In this interconnection process, we are mainly using copper as the material. But recently, further to copper, ruthenium also introduced for their better performance in very small scales. As we all know, when we are reducing the conductor size, it is going to be, when it is going to really smaller sizes, we know that resistance will be increased, then heat dissipation also will be increased in copper. But ruthenium is showing more good performance than copper in very low scales. Further to that, ruthenium is also not required any barrier layers in those connectors as well. Now here we can see that there are more than 15 to 20 layers on the top, and we use both ruthenium and copper as interconnects. We are using ruthenium for lower layers, most sensitive lower layers, and copper for higher layers. Key suppliers here are Tokyo Electron Japan and EMD Electronics Germany. As a whole picture, this front end part, which means creating transistor on the wafer and creating those interconnect layers using ruthenium and copper, those back end part, those front end and back end parts generally doing by those foundries like TSMC, Samsung or Intel foundries, those by those foundries. After all of these steps, now we are coming to some final stage. Here initially we have, in this final stage, initially we have to check whether these chips or integrated circuits are working well, because these are microscopic level elements and we can't see them in naked eye and we can't check them physically using our equipment. So there is a specific way, we are calling it as electrical dye sorting. Here actually some kind of diagnostic probe is connected to each of these die and doing some kind of diagnostic testing. And there are chips, which means integrated circuits, or dies which is going through this diagnostic test and passes. Those are going to category as a functional category. If those dies which is going to fail in category, they are going to discard category. The percentage which is properly functioning dies to total dies on the top of wafer, those percentage we are calling this as yield. Here you can see on the top of one wafer there are hundreds of these kind of dies. Same design, there are hundred of dies are there, which means there are hundred of chips on the top of the same wafer. And here in using electrical die sorting, we are sorting out functional and discarding dies. Then these functional dies are getting separated from wafer using laser dicing. Now we have created that our integrated circuit and diced out that required die or integrated circuit out. Nowadays those integrated circuits or chip are not in standalone chips. Now there are different chiplet architectures, which means input, output and some memory cells also together with these chiplets. And there is another architecture called chip on wafer on substrate to reduce the time which is going to transfer data from main processor to memories and those things. To reduce those things on the top of same substrate, we are creating both chip and memories and input output pairs on the top of same silicon interposer. By using these kind of things, further to that our functional chips, there are some partially functional chips also, then we can use those partially functional chips as memory or input output parts, and then we can improve the yield of the process as well using those partially functional things to input outputs and memory cells. Earlier mentioned process testing and assembly and packaging, those process mainly handled by OSAT finishers. OSAT means outsourced semiconductor assembly and testing companies. Those companies are AC Group Taiwan, Amkor Technology USA. Yeah, those are the companies who are governing these processes, testing, assembly and packaging processes. Now we have gone through full flow of grain of sands to chip inside our device. Initially we started with silicon dioxide, which are from Norway, Australia or United States, North Carolina. Then we got that silicon dioxide and stripped silicon away from that silicon dioxide. Then we receive metallurgical grade silicon. Since they are not still purified enough, then we created electronic grade silicon. From that electronic grade silicon, it is not having perfect lattice structure. Since we have convert that lattice structure into perfect lattice structure, and we finally came up with ingot, and we slices that ingot and create wafer slice. Then after polishing and all of these post-processing steps, we have came up with mirror-like wafer with extreme platinum. Then from other side, designers together with electronic design automation tool makers, IP designers with different instruction set architectures, they are initiated with design RTL code, and finally, or with all of the ecosystem help, they have came up with GDS2 or OSIS design files. Now we have perfectly polished wafer and these design files. Then we came to Taiwan with that mirror-like wafer and GDS file, which means design file. Then with the help of Dutch optics, we have printed our design on the top of wafer. Then we did our back-end fabrication part also. Finally, assembling, packaging, testing. We go through those steps. Then finally, this chip came into inside our phone and phone came into our pocket. So that is the full flow I want to explain. I think you got some kind of insight from here. If you are having any issue or concern, you can comment down in the below section. Or if you are having any kind of experience, you can share knowledge inside the comment section as well. If you need this kind of videos more, you can subscribe my channel and stay tuned with me. Thanks a lot.